Welcome to today's problem walkthrough. In this session, we will explore problem number 421, maximum XOR of two numbers in an array. This is an interesting problem where we delve into bitwise operations to find the maximum XOR value between any two numbers in an array. Let's get started. In this problem, we are tasked with finding the maximum XOR value that can be obtained by selecting two distinct elements from an array of integers. The input to the problem is an array called nums, where the size of the array can range from 1 to 200,000, and each element in the array is a non-negative integer, with a maximum value of 2 to the power of 31. The output is a single integer, which represents the largest XOR value achievable by any two distinct numbers in the array. To maximize the XOR result, we want to focus on the bitwise operation XOR, which outputs a 1 for each bit position where the bits of the two operands differ. This means that the goal is to choose numbers that maximize the most significant differing bits first, followed by the less significant ones, to achieve the highest possible result. Understanding how XOR works at the bit level is key to solving this problem efficiently. Let's look at an example to make the problem clearer. Suppose the input array is nums equals 3, 10, 5, 25, 2, 8. The maximum XOR value in this case is 28. This result is achieved by XORing the numbers 5 and 25. To understand why, we look at their binary representations. 5 is represented as 0000000101, and 25 is represented as 00011001. When we perform the XOR operation between these two numbers, we get 00011100, which is equal to 28 in decimal. This shows that by carefully choosing two numbers with the right pattern of differing bits, we can achieve the maximum XOR value. Now, let's consider another example. Suppose the input array is nums equals 0, 2, 7, 9. In this case, the maximum XOR value is 15. This maximum value is achieved by XORing the numbers 7 and 9. The binary representation of 7 is 00000111, and the binary representation of 9 is 00001001. When we XOR these two numbers, the result is 00001111, which corresponds to 15 in decimal. This example further illustrates how the XOR operation emphasizes the bits where the two numbers differ, and selecting numbers with the right differences can lead to the maximum result. Here's another simple example. If the input array is nums equals 1, 2, the maximum XOR value is 3. This is achieved by XORing 1 and 2. In binary, 1 is represented as 00000001, and 2 is represented as 00000010. Performing the XOR operation between these two values gives 00000011, which equals 3 in decimal. This demonstrates that even with a small input size, the problem remains consistent. The task is to select two numbers whose differing bits create the largest possible result. Finally, let's consider some important constraints and edge cases. If the array contains only two elements, the result will simply be the XOR of those two numbers, as there are no other pairs to consider. If the numbers in the array are very large, close to the maximum value of 2 to the power of 31, the XOR result could involve all 31 bits, which makes it crucial to have an efficient algorithm to handle such cases within the time limits. Additionally, if all elements in the array are identical, the result will always be 0, because XORing any number with itself results in 0. These edge cases highlight the importance of considering both the size and the values in the array when designing an optimal solution. To solve this problem, we initially considered multiple approaches. The most straightforward method is the brute force approach, where we calculate the XOR for every possible pair of numbers in the array and track the maximum XOR value. While this approach is simple to understand, it requires two nested loops, leading to a time complexity of n squared. This becomes infeasible for large input sizes, especially when the array can contain up to 200,000 elements, making it computationally expensive. To address this inefficiency, we explored an optimized approach using a tree. The intuition behind this method is that the XOR operation produces a 1 in each bit position where the two numbers differ, so to maximize the XOR result, we need to maximize these bitwise differences. By focusing on the binary representation of numbers, the tree allows us to efficiently find pairs of numbers with the desired characteristics. Specifically, we insert each number's binary representation into the tree and, for every number, traverse the tree to find the complement of its bits whenever possible, thus maximizing the XOR. This approach significantly improves efficiency with a time complexity of O(n*(w), where W is the number of bits in the binary representation, which is fixed at 31 for this problem. Additionally, the space complexity of the tree-based approach is O(n*(w), which is manageable given the constraints. This method was chosen because it leverages the properties of XOR and binary representation to minimize redundant computations while providing a structured and efficient solution. Another approach we considered was a hashing-based XOR method. The intuition here is to focus on the most significant bits first. By iterating from the highest to the lowest bit, we can use a hash set to store prefixes of numbers corresponding to the current bit length. Then, we check if any two prefixes can achieve the desired XOR value by using the property that the XOR of two prefixes equals the candidate result. This approach is also efficient, with a time complexity of O(n*(w) and a space complexity of O(n). However, while both methods are similar in their asymptotic performance, the tree-based approach was preferred because it provides a clearer and more direct mechanism for maximizing XOR by systematically examining the binary representations bit by bit. Ultimately, we chose the tree-based approach as it systematically builds the solution by fully utilizing the binary representation of numbers. The tree structure allows us to efficiently traverse and perform lookups, ensuring that we can maximize the XOR result one bit at a time. This method is not only scalable for large input sizes due to its O(n*(w) time complexity but also provides clarity in implementation. Compared to the brute force method, the tree is exponentially faster for large inputs, though it does require additional space. When comparing the tree to the hashing-based XOR approach, the tree stands out for its conceptual simplicity and its ability to directly focus on maximizing XOR without intermediate steps. In summary, the tree-based approach strikes an optimal balance between time complexity, space complexity, and ease of understanding, making it the most suitable choice for this problem. The goal of this problem is to find the maximum XOR value that can be obtained by any two numbers in an array. XOR, or exclusive OR, is a bitwise operation that compares the bits of two numbers. It outputs 1 if the bits are different and 0 if they are the same. To begin, we can approach this problem with a brute force method. First, we initialize a variable called max_XOR to 0, which will keep track of the largest XOR value we encounter. Next, we use two nested loops to examine every unique pair of numbers in the array. The outer loop selects one number, and the inner loop compares it with all subsequent numbers in the array to avoid duplicate pairs. For each pair, we calculate their XOR value and check if it is greater than our current max_XOR. If it is, we update max_XOR. Finally, after evaluating all pairs, we return the maximum XOR value found. While this method is straightforward, it's inefficient for large arrays due to its time complexity of O(n²). To improve performance, we turn to an optimized approach using a data structure called a tree, which is specifically suited for working with binary representations of numbers. To optimize the solution, we first convert each number in the array to its 32-bit binary representation. This ensures that all numbers are represented with a consistent bit length, which is important for building the tree. A tree is a tree-like data structure where each node represents a bit, allowing us to efficiently store and query binary numbers. To construct the tree, we start with an empty root node. For each number in the array, we insert its binary representation into the tree one bit at a time. A 0 in the binary number branches left, while a 1 branches right. After building the tree, we calculate the maximum XOR value by traversing the tree for each number in the array. The goal during traversal is to maximize the XOR contribution from each bit. To do this, at each level of the tree, we attempt to follow the branch opposite to the current bit in the number, as this maximizes the XOR at that position. For example, if the current bit is 1, we look for a 0 in the tree. If the opposite branch is unavailable, we follow the same branch. As we traverse, we accumulate the XOR value and compare it to the global max_XOR, updating it if the new value is larger. Once all numbers are processed, the global maximum XOR value is returned. Let's explore some key insights that make this approach work. First, XOR achieves its maximum value when the bits of two numbers differ as much as possible. For instance, the XOR of 1010 and 0101 is 1111, which is the highest value obtainable for 4-bit numbers. This principle guides our traversal of the tree, where we aim to choose the opposite branch for each bit whenever possible. Next, instead of testing every pair of numbers explicitly, the tree structure allows us to efficiently find the best possible pair for a given number. By navigating through the binary representation, we avoid the inefficiencies of the brute force method. In terms of time complexity, the brute force approach requires O(n)² operations, as it involves nested loops over the array. However, the tree-based solution is much faster, with a complexity of O(n*L), where n is the size of the array and L is the bit length, which is 32 for 32-bit integers. This makes the tree method significantly more scalable for large arrays. The tree plays a central role in the optimized solution. It's a hierarchical data structure where each node represents a bit, either 0 or 1. This structure enables efficient storage and querying of binary numbers. One of the key reasons for using a tree is that it allows us to find the optimal XOR pair for a given number in O(L) time, where L is the bit length of the numbers. The two main operations on the tree are insertion and querying. During insertion, we add the binary representation of each number to the tree, bit by bit. During querying, we traverse the tree to find the number that maximizes XOR with a given number by choosing branches that differ from the current bit whenever possible. It's also important to consider edge cases. For example, if the array contains only one number, the maximum XOR will be 0, since XORing a number with itself always yields 0. If all numbers in the array are zeros, the result is also 0, as the XOR of any two zeros is 0. For negative numbers, we need to ensure their binary representations are handled correctly using 2's complement. Lastly, the tree structure is efficient enough to handle large inputs, up to the problem's constraints of 2*10 to the power of 5 elements. To understand the optimized approach better, let's walk through an example. Suppose the input array is 3, 10, 5, 25, 2, 8. First, we convert each number to its 8-bit binary representation for simplicity. 3 becomes 00000011, 10 becomes 00001010, and so on. Next, we build the tree by inserting each binary representation into it. Each bit is added level by level, branching left for 0 and right for 1. Once the tree is built, we calculate the maximum XOR for each number. For example, when processing the number 5, binary 00000101, we traverse the tree to find the number that maximizes XOR with it. At each bit level, we try to take the opposite branch for the current bit, as this maximizes the XOR contribution at that position. If the opposite branch doesn't exist, we take the same branch. By repeating this process for all numbers, we find that the maximum XOR value is 28, which comes from XORing 5 and 25. This demonstrates how the tree simplifies the search for the optimal pair, avoiding the need to explicitly compare every pair in the array. Finally, let's summarize the complexity of our approach. In terms of time complexity, the brute force method requires O(n)² operations, as it involves comparing every pair of numbers in the array. In contrast, the optimized tree-based solution has a time complexity of O(n*L), where n is the size of the array and L is the bit length, which is 32 for 32-bit integers. This makes the tree method far more efficient for large arrays. The space complexity of the optimized solution is O(n*L), as the tree requires storage for the binary representations of all numbers. This is manageable even for large input sizes, as the bit length is fixed at 32. Overall, the tree-based approach strikes an excellent balance between performance and scalability, making it a practical solution for finding the maximum XOR of two numbers in an array. To solve the problem of finding the maximum XOR of two numbers in an array, we start by defining a class called solution with a method named findMaximumXOR. Inside this method, we initialize two variables, max_XOR, which will keep track of the maximum XOR we've found so far, and mask, which is used to progressively isolate the most significant bits as we iterate through the numbers. The algorithm iterates over the bit positions from the most significant bit, which is 31, down to the least significant bit, 0. For each bit position, we update the mask to include the next bit by performing a bitwise XOR operation with one shifted left by the current bit index. This allows us to focus on the prefixes of all numbers up to the current bit position. These prefixes are stored in a set to ensure uniqueness, and we compute them by performing a bitwise AND operation between each number and the current mask. Next, we calculate a tentative maximum XOR value by setting the current bit in max_XOR to 1. At this point, we need to determine if this candidate value is achievable by checking if there exist two prefixes in the set whose XOR equals the candidate. If such prefixes are found, it means the candidate XOR value is achievable, so we update max_XOR to this new value. By iterating through all the bit positions in this way, the algorithm ensures that we are always building the maximum possible XOR value one bit at a time. Finally, after completing the loop, the method returns the maximum XOR value found. This approach is efficient, as it leverages the properties of prefixes and bit manipulation to narrow down the search space, avoiding the need for a brute force comparison of all pairs of numbers in the array. In this Java implementation, we start by defining a class called solution and a method named findMaximumXOR, which takes an array of integers called nums as input. To begin, we initialize two variables, maxor to store the maximum XOR value, initially set to 0, and mask, which helps us isolate specific bits during the computation, also starting at 0. The key idea here is to iterate over all bit positions, starting from the most significant bit, which is bit 31, down to the least significant bit, which is bit 0. For each bit position, we first update the mask to include the current bit. This is done using a bitwise XOR operation with a left-shifted value. The mask allows us to collect prefixes of all numbers in the array, where each prefix represents the numbers with only the higher bits considered, discarding the lower bits. These prefixes are stored in a hash set to ensure uniqueness. Then, we assume a potential maximum XOR value, called candidate, by setting the current bit to 1 in the existing maxor. This represents our tentative goal for the maximum XOR at this step. To verify if this candidate is achievable, we check whether there exist two prefixes in the set whose XOR equals the candidate value. This is the central part of the logic, as it determines whether the current bit can be set in the final result. If we find two prefixes in the set that satisfy this condition, it means the candidate XOR is achievable, and we update maxor to this new value. Otherwise, the current bit remains unset in maxor, and we move to the next lower bit position. This process continues iteratively for all 32 bits, ensuring that we maximize maxor bit by bit. By the end of the loop, the maxor variable holds the maximum XOR of two numbers in the array. Finally, we return this value as the result. This approach is efficient because it leverages bitwise operations and the properties of XOR, and it avoids explicitly comparing all pairs of numbers. The use of a hash set to store prefixes ensures that the solution remains performant even for large input arrays. To solve this problem, we aim to find the maximum possible XOR between any two numbers in the array. We start by initializing two variables, max_XOR, which keeps track of the highest XOR value we've found so far, and mask, which helps us isolate the more significant bits of the numbers progressively, starting from the most significant bit. In the first iteration, where I equals 31, we update mask to include only the 31st bit, which is the leftmost bit in a 32-bit integer. This results in mask being 10000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 the bitwise AND operation between each number in the array and the mask. For this iteration, all the numbers in the array result in 0 when masked, so prefixes is 0. We then calculate a tentative candidate for the maximum XOR by setting the current bit in max_XOR to 1. However, since no pair of prefixes satisfies the condition to achieve this candidate, max_XOR remains 0. In the next iteration, with I equal to 30, the mask is updated to cover the two most significant bits, resulting in mask being 11000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. Again, the set of prefixes remains 0, and no valid pair is found to achieve the new tentative candidate. Thus, max_XOR remains unchanged at 0. As we progress through the iterations and narrow down the bits, we start to observe changes in the prefixes. When I reaches 4, the mask becomes 111111111111111111111110000, which isolates the top 28 bits of the numbers. At this point, the set of prefixes becomes 0, 16, 8, 24. The tentative candidate is 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000For prefix equals 16, we find that candidate prefix equals 8, which is also in the set of prefixes. This confirms that the tentative candidate can be achieved, so we update max_XOR to 16. In the next iteration, with I equal to 3, the mask is updated to 1111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111. The tentative prefixes becomes 0, 8, 24. The tentative candidate is 0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 and this time, for prefix equals 24, we find that candidate, which is in the prefixes set. As a result, we update max_XOR to 24. By continuing this process for the remaining bits, we eventually determine that the final value of max_XOR is 28 after the last iteration. In the second example, we apply the same approach but with a new set of numbers, 14, 70, 53, 90, 32. We start with max_XOR set to 0 and initialize mask to 0. As we progress from the most significant bit downwards, we observe that initially, the set of prefixes remains 0 for several iterations, and no valid pairs are found to update max_XOR. However, when we reach I equal to 6, the mask becomes 1111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111. At this point, the tentative candidate is 01000000000, and we find that the prefix 64 satisfies the condition, allowing us to update max_XOR to 64. This demonstrates how the mask helps isolate progressively smaller groups of bits and allows us to find achievable XOR values. Continuing with the second example, when I equals 5, the mask becomes 111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 The tentative candidate is 011000000, and here, the prefix 96 satisfies the condition for achieving this candidate, so we update max_XOR to 96. As we continue refining the solution through the remaining iterations, we narrow down the bits further and find that the final value of max_XOR becomes 127. This demonstrates how the algorithm systematically builds the maximum XOR by leveraging the prefixes and the mask at each step. In the third example, the array of numbers is 0, 1, 2, 3, 4, which consists of simple binary increments. The approach remains the same. We initialize max_XOR to 0 and progressively refine it as we iterate through the bits from most significant to least significant. Since these numbers are sequential, the prefixes evolve in a straightforward way, and we find that the maximum XOR value is achieved by pairs like 4, 3. This pair produces an XOR of 7, which is the highest possible for this array. Thus, the final output for this example is 7. The time complexity of this algorithm depends on two factors: the number of elements in the input array, denoted as n, and the number of bits required to represent the largest number in the array, which we refer to as L. For integers in a 32-bit system, L is fixed at 32. The algorithm processes each bit position from the most significant bit to the least significant bit, which contributes O(L) to the complexity. Within each bit position, it computes the prefixes for all numbers in the array. This involves performing a bitwise AND operation on all n numbers, making this step O(n) for each bit. Additionally, the algorithm checks for pairs of prefixes that satisfy the XOR condition, which involves iterating through a set containing at most n prefixes. Since set lookups and XOR operations are constant time, this step is also O(n) per bit. Combining these, the overall time complexity becomes O(L*n). For 32-bit integers, L is constant, so the complexity simplifies to O, n. The space complexity of the algorithm is primarily influenced by the storage requirements for variables and the prefixes set. Variables such as max_XOR, mask, and temporary values require a constant amount of space, contributing O(1). The prefixes set, however, can store up to n elements, where each element is a binary prefix requiring L bits. For 32-bit integers, each prefix requires 4 bytes, so the space complexity of the set is O(n). When we combine these factors, the overall space complexity of the algorithm is O(n). Since the algorithm processes all L-bit positions and all n elements in every case, whether best, average, or worst, the time complexity remains O(n), which simplifies to O(n) for fixed-width integers like 32-bit numbers. The optimized approach significantly improves upon the brute force method. In the brute force approach, the algorithm iterates through all possible pairs of numbers in the array and calculates their XOR, resulting in a time complexity of O(n²) due to the n*(n1/2 pairs. The optimized solution reduces this by using bit manipulation and is set to progressively compute results. Instead of evaluating every pair, it processes each bit position individually and keeps track of prefixes, reducing the time complexity to O(n) for 32-bit integers. This is a substantial improvement. Mathematically, with L fixed at 32, the bitwise iteration contributes a constant factor to the complexity. For each bit, the algorithm processes all n elements and performs constant time set operations, making the overall complexity proportional to n. Thus, the time complexity is O(n), and the space complexity is O(n), reflecting the storage needed for the prefixes set. When tackling XOR problems, there are a few common mistakes to watch out for. First, misunderstanding the unique properties of XOR can lead to overly complex or incorrect solutions. Remember, XOR has properties like x(x = 0 and x(0 = x. These can simplify your logic significantly. For instance, instead of iterating through all possible pairs to find the maximum XOR, you can use structures like a tree or optimize with bitwise manipulation. Another frequent pitfall is ignoring negative numbers. Some solutions assume all inputs are non-negative, which can cause incorrect results if negative numbers are present. To avoid this, ensure your algorithm handles the entire range of integers. Lastly, overlooking edge cases can trip you up. Arrays with only one element, arrays where all elements are identical, or arrays with a mix of very large and very small values may expose flaws in your solution. Testing these edge cases explicitly will help you catch such issues early on. Another mistake to address is relying on inefficient brute force solutions. While brute force approaches can work for small inputs, they often require O(n²) time, which becomes impractical for larger datasets. Instead, explore optimized techniques like using tries or leveraging bitwise operations. Additionally, when implementing a tree for XOR-related problems, incorrect construction or traversal logic can introduce subtle bugs. For example, if you don't handle the binary representation of numbers correctly during insertion or fail to account for edge cases in traversal, your tree might not produce the expected results. To prevent this, carefully debug and verify each step of your tree implementation, ensuring it aligns with the problem requirements. Now, let's discuss some insights specific to interviews. One key takeaway is that XOR problems often revolve around bitwise operations, so it's essential to have a solid understanding of binary representations. Interviewers frequently expect you to move beyond brute force solutions and propose optimized approaches like using bitwise techniques or data structures such as tries. Additionally, you should be ready to explain the trade-offs. For example, a tree-based solution is typically faster than brute force in terms of time complexity but may use more space. It's also common for interviewers to present follow-up questions, such as modifying the problem to find the XOR for subarrays or applying constraints like finding the maximum XOR within a specific range. Finally, it's helpful to familiarize yourself with related problems, such as LeetCode 136, 260, or 137, as they often share similar concepts and techniques. There are several approaches you can consider when solving XOR problems, each with its own trade-offs. The brute force method involves computing the XOR for all pairs of elements and tracking the maximum. While this approach is simple to implement, it has a time complexity of O(n²), making it inefficient for large inputs. A more optimized approach is to use a tree to store the binary representations of the numbers. This method allows you to efficiently compute the maximum XOR using O and *W time, where W is the number of bits, typically 32. However, it does require additional space to store the tree. Another alternative is the bitwise iteration approach, which involves iterating through the bits from the most significant to the least significant to greedily construct the maximum XOR. This method also has a time complexity of O and *W, but avoids the extra space overhead of the tree. While slightly less intuitive, it's a great option when minimizing space usage is a priority. Great job! We've summarized the key points of the session, including the brute force approach and its implications. Remember to practice similar problems to strengthen your bit manipulation skills. Thank you for joining, see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!